Here we go. So the first one, so let me jot down some techniques down here. What is it? Shoot. Where I am here. My pen doesn't work. Let's try now. Okay, so first strategy. Get everything into sine and cosine. These don't all apply to every problem, but here are some strategies for certain problems. So get everything in terms of sine or cosine. It's not divided by. Okay, this particular strategy works very well on number one. Okay, so for number one, how can we turn everything into sine or cosine? We already got cosine squared. Tangent squared is sine squared over cosine squared. And lo and behold, we have a very nice simplification there. This integral just becomes sine squared. Second strategy. No sine squared and cosine squared. This is probably, for this section, this is the most important integral in the section. Know how to integrate sine squared and likewise know how to integrate cosine squared. Did anyone learn how to do that over the weekend? How do you integrate sine squared? Half angle formula. To integrate sine squared or cosine squared, you're going to use the half angle formula. So for sine squared, it is 1/2 1 minus cosine 2x. So this is just one that you know, because this will come up a lot. The integral of sine squared, or the integral of cosine squared, or a slight variation on those. Use the half angle formula. And then if it's cosine squared, the only difference is plus right there. 1/2 1 plus cosine 2x. So we can pull the 1/2 out in front, and we got an easy integral here. Antiderivative of 1 is x. Antiderivative of cosine 2x is going to be 1/2 sine 2x plus c. If you want to distribute that 1/2 or leave it like that, doesn't matter. You could have 1/2 x minus 1/4 sine 2x. Okay, questions on, I don't care about grading. I care about you learning this. Questions on how to do this one? Yeah?
So to get the
You see it? Yeah. You're good? Other questions on number one? Yes, sir?
What if you change tangent square x to secant square x minus 1?
Uh-huh.
And then you distribute cosine
right.
square x to secant square x and minus 1.
And you got 1 minus cosine squared. Same thing. Yeah, so then you end up doing cosine squared instead of sine squared. So it's something slightly different, but that's valid. It's just a little more work, right? This is more direct. But yeah, that's valid. Totally valid. Other questions about this one? No, just squared. Just sine squared or cosine squared. Well, I guess yeah. If you have it to the fourth, you end up doing this. You break it into 2 half angles and you FOIL it out. Yeah.
I don't know if this is the best example of one, but sometimes I didn't really on the homework at least. Like I wouldn't know where to start. Like which trig identity is there a way to know without?
I'm giving you some strategies. Yeah. So you just have to kind of have some experience, and you just try at them, and then you start gaining some experience, and you can do it. But I'm going to give you some strategies here. Okay. Other questions on number one? Okay, so what's the key to sine squared or cosine squared? One more time. Half angle formula, or identity. Are we good? Okay, number 2. Okay, so let's see if I can leave the strategies up there. So what's faster? Going fast and coming back and cleaning up the mess, or going slow and not missing anything? Okay. All right. Jerks. All right. Sine 2x times cosine x dx. Okay. So this is just screaming for us to do what? So here's the thing. When you have different arguments, that causes problems. We can't really do an antiderivative if you have different arguments, meaning what's going into sine here is different than what's going into cosine. Here the angle 2x is going in. Here the angle x. It kind of stops us from making any progress until we get all the arguments to be the same. Okay? So we can deal with that by changing sine 2x to 2 sine x cosine x. We use that identity. And then the cosine becomes cosine squared. Third strategy. Look for, what do we have now? What applies? How can we make progress on this? Undoing chain rule. Why? Because I really have here what cosine, you have to see them this way. And so look, I have what's outside here is essentially the derivative of the inside function. That's exactly what we need for undoing chain rule, right? And so our first attempt is, we're going to do the antiderivative of, of something squared, right? We're going to leave cosine as it is. We have a 2 out here also. So we have the 2 times 1/3 cosine x cubed. And then we have to check it and see if it matches our original thing. So if we check this, check it in red, we get a negative, right? So it'll be 2 times cosine squared times negative sine x. That's our check. And that's only off by a negative sign, right? So then we come back here, boom, and we got it. Okay, I care about you learning this, not grading. So ask me, yeah.
We do it anyway, and you can still get that answer. It's okay.
Yeah, as long as you're not using technology.
Can
Yeah.
you just explain where your mouse is, that step to the bottom one?
This one to this one?
Yeah.
So I'm recognizing that this is undoing the chain rule because I have a composite function, and this other function out here is the derivative of the inside. That's a perfect setup for the undoing the chain rule. Because sine is essentially the derivative of cosine. So this is my g prime f, and I just need to do the antiderivative of g, which is 1/3 to the third. That's antiderivative, leaving the inside the same. And then when I did the check on it, all I needed was a negative sign.
Alright, thank you so much.
Sure. Yeah.
So whenever we see 2 trig intervals multiplied together, do we always need an identity?
I wouldn't
So,
say
like,
that.
Not always, but you kind of like usually do use these.
Well, yeah, most of them deal with identities. Not all of them, but most of them you're working with identities to change the form so you can get something that you can do.
Because I noticed by the parts one, we only have like one identity and then
Rarely do we see an overlap between these trig integrals and the undoing the product rule. Is that what you said? Yeah, rarely we see undoing the product rule and these trig entities like both in the same. But undoing the chain rule permeates all of the techniques. Undoing the chain rule, we see through all the techniques. Other questions? Yeah.
Would integration by parts have worked for that?
No, so that's the same. That's what we're calling undoing the product rule. So maybe, I guess maybe, I don't know. It might work. Yeah, sine times cosine. It didn't work. Okay. So usually trig identities will be a faster track than undoing product rule. That's a longer, kind of more complicated process. So if you can get it to work with identities, that's what we want, because that'll be a faster track to the answer. Other questions? Yes, sir?
There's some table of integrals in the back of the book.
Uh-huh.
Are those sources that we can use?
It doesn't get you off the hook from knowing how to do these. I mean, there's certain ones that are appropriate for using a table, but all the ones we've learned so far, you have to know the techniques without using a table. But then there's actually a whole section on how to use the tables to do like harder ones. But the ones we've done so far, you're responsible to be able to do without the tables. Yeah. Other questions? Okay, let's look at number 3. And number 3 brings us to our fourth strategy. Not just look for undoing the chain, but set it up. So set it up yourself for undoing the chain. And that's this last one. So we see we got a bunch of secants and a bunch of tangents. And so we think, okay, where is there a derivative kind of hiding in there? Where in there is there a derivative hiding so that I could, like, if I could just isolate something that's the derivative of what's happening in the other part of the integral, then I can kind of like force undoing the chain rule to occur. So, yeah, right. So the derivative of tangent is secant squared. So if I can pull out a secant squared and get the whole rest of the integral in terms of tangent, then I'm like forcing it to be undoing the chain rule. Does that make sense? Also, let me show you. Okay, so I'm going to pull out secant squared.
Are you able to pull it out in front of the intervals?
No, not if it has x's in it. Only if it's a constant. Yeah, if it has x's in it, no, that's part of the function. Yeah, I mean, then every integral would just be 1, if you could do that.
No, I know that.
Anything that's got an x has to be part as a function. So, all right, so we're thinking, okay, the derivative of tangent is secant squared. So if I can get this to be secant squared times a whole bunch of stuff with tangents in it, then I can do undoing the chain rule. So I pulled out secant squared. What's left? Another secant squared, which we have an identity to change it to tangent squared, which is 1 plus tangent squared. So that's the remaining 2 factors of secant that I had when I pulled out the secant squared. And then I also have this tangent to the 7th. So this is right here is the secant squared. Now all I need to do is distribute inside those big brackets, and I have 2 terms that are both functions of tangent, and then they'll both be times secant squared, so I'll just have undoing the chain rule twice. So I'll have secant, this will be secant squared times tangent to the 7th. And then plus secant squared times tangent to the 9th. Okay, did you see what happened? Any questions? Catch that? So I distributed the tangent to both of these, the tangent to the 7th, and then I distributed the secant squared to both of those. So this was secant squared times tangent to the 7th, and then secant squared times tangent to the 9th. And now look, I've got this to the 7th, and then I've got this one to the 9th. And so I'm home free, because why? Because secant squared is the derivative of tangent. Secant squared is the derivative of tangent. So, undoing the chain rule, I'm going to do the antiderivative of something to the 7th, which is 1/8 tangent x to the 8th. And then this will be, what, 1/10 tangent x to the 10th. Okay, questions on this one? So there's these types also with sine and cosine, right? We know that sine is the derivative of cosine, etc. So in these complicated ones with sine and cosine, what are you going to pull out? You'll just pull out a single sine and then try to get the rest in terms of cosine. Or you'll pull out a single cosine and try to get the rest in terms of sine. Okay, question?
I've never really done that through the chain rule too much. I just did use substitution.
Yeah.
It's technically the same thing, right? Because you're pulling out
Yeah,
tangent,
it's
tangent
just-
B or U, and then your D or
Yep.
DC.
If you learn use substitution and you want to do that, that's fine. It's just if you learn undoing the chain rule and you really get good at it, you can do it in half the time as you sub. That's what I'm encouraging you to do.
I still don't really see how the distribution works in the first step.
From here to here?
Yeah.
Okay, so imagine just distributing a tangent in. What would you have? You'd have tangent to the 7th
Yeah.
and tangent to the 9th.
Oh, okay.
So you just have tangent to the 7th and tangent to the 9th, and now each of those times secant squared.
All right.
Yeah. Other questions? Okay, so like I was saying, this thing here, the setup. So if you had like a bunch of sines and cosines, then what would you do? You would just want to pull out one sine, right? Because the derivative of cosine is sine. Or pull out one cosine, and then try to get the rest in terms of the other one instead of secant squared. We did secant squared because that's the derivative of tangent. So if you had a bunch of sines and cosines, you would just want either just one sine and the rest cosines, or one cosine and the rest sines. And then you're setting yourself up for undoing the chain rule. Last questions. Okay, so let's score it. Ready? Write 20 out of 20 on the top of your page. And then hold on to it for your notes. Yes. But you will get the points. You'll get the points. What's that?
Tangent squared is also equivalent to secant squared.
Yep.
So what I did was I did tangent squared. So right there on the left, and then I did it in terms of secants. And then I brought out one.
There's no tangent squared to the 4th here. How'd you get tangent squared to the 4th? It'll be tangent to the 8th.
Tangent squared to the 4 is the same as tangent.
Show me after class. After class. Okay, so based on these 3 examples, we'll have some more web work over the weekend on this type, along with the new type that we're going to do. Okay, so you get more practice on these. All right, yeah, and then maybe Monday we'll have a real quiz. Okay.
I'm looking on your syllabus for when this is going to be, but you'll have.
Yeah. So the test would be the very earliest would be a week from tonight, but I'm thinking it's going to be the following Monday, a week from Monday, a week from this coming Monday instead of a week from tonight. But if it were a week from tonight, I would email you tomorrow to let you know that. How about that? Okay. Yeah. So you have plenty of warning. But we can. I'm pretty confident it can be a week from Monday. Is that fair? What? What's that?
Yeah, that's actually perfect.
Oh, well, this is college. I haven't decided. What, the final exam? The final exam? I don't know. I think it's according to the normal schedule for ASU. What's that? Okay. Okay. If you need to know immediately, then just email me, and I can let you know. But I think it's according to the normal ASU schedule of finals. You can go to the final exam schedule on ASU, and you can look it up. Or if you can email me, and I'll have to do that for you. Okay. Other questions? Okay, so we want to do the next one, which has to do with so rational functions. So what is a rational function? That's the rational functions are the ratio, right? Ratio of 2 polynomials. Or fraction of 2 polynomials. Okay, and so the just type, it'll be easier. So for these, the first thing you want to say is if the degree of the numerator, I'll make that bigger. So if n is bigger than, so by this I mean the degree. So if the degree of the numerator is greater than or equal to the degree of the denominator, like the highest power of the polynomial, okay, then you're going to begin by long dividing. The fraction okay, and then if the denominator can be, let's do this. If the denominator can be written as a product of factors, this is the main technique we're going to learn. You're going to decompose the fraction into the sum of partial fractions. So what does that mean? So that the denominator in your rational function, if you can factor it out into factors like parentheses, right? Then that's kind of the key, or that's kind of the indicator that you're going to use this partial fractions technique. You're going to take that big fraction then, and you're going to split it up into the sum of many fractions. And then each one of those fractions would be a much simpler or a doable antiderivative by what we've learned so far. That's the idea. So we're going to take, here's the big picture. We're going to take a big fraction, we're going to split it up into many fractions, and then do each one separately. Okay? That's the idea. Okay? So, for example, integral 2x cubed. So this is what a rational function looks like. It's the ratio or a fraction of two polynomials. So we look, is the degree of the numerator bigger than or equal to the degree of the denominator? Yes. So we have to long divide. Okay? So now, if you've never long divided before, I can't take the time to actually teach this. I'm just going to do it, and then you'll have to, outside of class, get help to do this. It's something you should know from pre-calc and advanced algebra. But you basically do the same thing you do when you long divide just numbers. Okay, so try to follow it if you've never seen it before, and then I'll be happy to help you later. So we're going to write out that numerator as, with all its terms, 0x squared, 0x, and 0. And then so we're asking now, what am I going to multiply x plus 1 by so that I can subtract away 2x cubes, right? 2x squared. So that'll go above the x squared here. And so that'll be 2x cubed plus 2x squared. And then when I subtract, no reciprocal.
Not the reciprocal, I mean, make it negative.
Yeah, we're going to subtract that now. Yeah. So that's 0, that's what we wanted, and now this will be plus, right? Because you're subtracting, plus, minus 2x squared. And so now we're asking, okay, now I want this to subtract away. So what I'm going to multiply x plus 1 by, so this goes away. And negative 2x. Oh, I have to bring down a 0x, right? Bring down the 0x. And then I'm going to get minus 2x squared minus 2x. I'm going to subtract, and that'll be 0, and that'll be plus 2x. And I'm going to bring down 0. Last time, what do I multiply x plus 1 by so I can get the 2x's to go away? Plus 2. 2x plus 1. When I subtract, I get negative 1, which is the remainder. Negative 2. Thank you. So my remainder is negative 2. Therefore, I can write that as the quotient plus the remainder over the divisor, right? So this whole thing is the same as 2x squared minus 2x plus 2 minus 2 over x plus 1. And that's equivalent to what we started with. Okay, so now the idea is that this we would be able to do, and this one we can. So I'll do it in red so it stands out. So it would be 2/3 x cubed minus x squared plus 2x. And then what is general structure of this antiderivative? Natural log, so minus 2 natural log absolute value x plus 1 plus c. Okay, so that actually did not involve anything to do with the partial fractions technique. Okay, that was just the long division by itself took care of it. The long division gave us something that we could just do the antiderivative of. So we never got to step 2. Sometimes you'll do this long division, and now this last fraction right here will apply, the partial fractions technique will apply to that last fraction. Okay. Is there a question?
I was just wondering why the partial fractions doesn't work for that situation.
Because you can't parse it apart because you only have this one factor of x plus 1 on the bottom. So in order to use partial fractions, you need a product of factors in the denominator.
Oh, right.
So there's just x plus 1. You can't. It's only one. It will always only be one fraction. Okay. So that's that one. So that one, just long division just did it. And so since you need some long division in some of these, I wanted to give you an example of long division. What will happen sometimes is after you do the long division, this remaining fraction will require the technique that we're about to do. Okay? So you'll have to do both. You have to long divide, and then you'll be left with a problem where you have to do step 2, which is what we'll spend the rest of the class doing. One's like step 2. Are we good? Does it make sense? Okay. So let's do the next example. Five x plus 1. Two x squared minus x minus 1. So, how about degree? Is the degree of the numerator greater than or equal to the degree of the denominator? No. Okay, so we're going to move on to step 2. So then, in order for this partial fraction thing to work, this needs to be able to factor into at least two factors. It needs to separate out into one thing times another. And so if it doesn't, then we can't use this technique. So the question is, does it? Okay, so everyone should know how to factor that. So we know we're going to have a 2x and an x, and then we need a plus 1 and a minus 1 so that the middle term is minus x. So plus or minus here? Plus here, minus here. Okay, so now we've got the right situation for this thing called partial fractions. Okay? So sometimes these, if it's rigged just right, you could undo the chain rule. If this, was the derivative of this down here. But it's clearly not, because so the factors won't work out. This would be 4x minus 1. We've got 5x plus 1. So there's no way that could work. Can't get that to work, okay? So even though you have a rational function, sometimes those are rigged for undoing the chain rule, and you don't want to do this. This is longer and more complicated. So keep looking for undoing the chain rule, okay? But we don't have that here. So what we're going to do is we want to rewrite this as a over 2x plus 1 plus b over x minus 1. So you know how you add fractions, right? You get a common denominator. So this is like adding fractions. We're going backwards. It's like unadding them in that you have the common denominator, and it's like, what are all the possible original denominators you could have had such that this was your common denominator? Well, you would have had a 2x plus 1 and an x minus 1. And then common denominator of those two, when you added them together, would be the 2x plus 1 times x minus 1. Okay? So we got to figure out then what are a and b so that this is equal to what we have. And then we'll be home free. That'll be an easy antiderivative. We'll just do that one and that one separately. So what are a and b so that it equals that? So what are we going to do? We're going to now proceed to add the fractions. Proceed to add them to make it look back like what we started with. Okay? So we're going to add these together. How do we add? Well, to add the fractions, you have the common denominator. And then what are we doing here to get our common denominator? Top and bottom by x minus 1. So that's going to give us, in that first fraction, a times x minus 1. And then what do we multiply top and bottom by here? 2x plus 1. So we'll have b times 2x plus 1. So all of these here that I put in red here, so this, my black box there, these are all equal. We just got to figure out, all those are equivalent. They're all the same thing. We just got to figure out what value of A and what value of B do it, right? Make it equal to what we started with. Okay, so how am I going to do that? Well, I've got the denominators the same, so I just need to get the numerators the same. So I'm going to multiply this out and get it to be, get the values of A and B so that we get 5x plus 1 in the numerator. Do you see? So I need A times x minus 1 plus B times 2x plus 1 to equal 5x plus 1. And then I've got it. So when I multiply everything out, I'm going to have ax plus 2bx minus a plus b equals 5x plus 1. So we just do this one coefficient at a time. What's the coefficient of x? And 5 is going to be the same as a plus 2b. Right? If I factor out an x, I'd have a plus 2b. So a plus 2b has to be 5, the coefficient of x. And then our constant, right? So this whole thing is our constant, and that's equal to? Right. Opposite of a plus b has to equal 1. So that's... And now we have a system, and however you know or want to solve that system, elimination, substitution, matrix method, however you prefer solving a system of equations. In this case, 2 equations, 2 variables. You should all have plenty of experience doing that in other classes, previous math classes. This one is just totally set up just to add them together and the a's go away. See that? So it's just all rigged for if we add everything, a's back at 0 plus 3b equals 6, b equals 2. Plug it back into one of these to get your a, which becomes b is 2, that's 4, a is 1. So what do we do? We found the values of a and b that make this form, the partial fraction or the decomposed form, equal to what we started with. If a equals 1 and b equals 2, then that is exactly the same expression or equal to this expression. So then we can do a 1 over 2x plus 1 dx plus 2 over x minus 1 dx. So
The partial fractions is the integral as well.
what's that?
The second box thing in red. That's
This
the
one?
integral as well. Oh, yeah.
I know it's just this. I just grabbed this. We're taking the integral of this expression and we're rewriting that expression. So this is my first step, rewriting that expression. And then that is that. And then this solved for the a and the b. Is that good? Okay, so then last step, 1/2 natural log absolute value 2x plus 1 plus 2 natural log absolute value x minus 1 plus c.
1/2 came from the 2x.
Yep, so it's kind of like a mini undoing the chain rule. We know it'd be ln of this, and then we think, oh, if we took the derivative, we'd get a factor of 2 that we don't have. Right? So that's like a mini, like a mini undoing the chain rule. And hopefully we're doing those in our head now. Okay. Did I lose anybody? So there are a lot. Yeah. Is there? Yeah.
I don't quite understand how you got from the right where your mouse is to right below there.
Here. So this is my numerator, right? That I got with a a and b has to be the same as 5x plus 1. So just gathering all the. I'm gathering all the terms with x and all the constant terms.
Okay.
So what has an x? There's a x of a and there's a 2b. So that has to be the a plus the 2b has to be 5.
Okay, you can separate.
Yeah, we're separating out by term, right? So we're going to separate the x's and then the constant terms. We have a negative a and a positive b, and that's got to be total up to 1. Yep. So we're separating out apples and oranges and then setting like things equal. Other questions? Okay, another example. So there's variations on this, more complicated. This is a real easy one. We need to get some way harder. So this one's already, the denominator is already factored. So it's just screaming at you. This is partial fractions, right? This is partial fractions because you've got a factored denominator already. So we have to come up with what are all the possible fractions that we have to consider that would have this as the common denominator. Question?
Yeah, so do you want us to do the product of the factors here, even though if you multiply the denominator out?
Yeah, then that's a long, ugly polynomial that won't help. I mean, there's a slight chance that it would be perfect for undoing the chain rule if that was a derivative of that, but very, very unlikely. Yeah, the fact that this is factored like this is just, it's just saying partial fractions. That's what you're going to do on this one. So one possible denominator could be just x minus 3. Another possible denominator could just be x minus 2. But then there's one more. There's one more denominator that just these two don't take care of. Okay? X minus 2 squared. So this is all the possible kind of exclusive denominators that could possibly have numerators that when you added them together you would get that single fraction. Okay, so then you say, well, what about x minus 3 times x minus 2? Well, that's taken care of by these two together. So you don't need another one that's x minus 3 times x minus 2 because that's redundant to these two added together. Do you see? Question?
Where did the just x minus 2 come from?
We need all possible denominators that would have this as the common denominator. So we kind of think backwards from adding fractions. Right? So when you add like 9, something to like 2/9 plus 8/3 plus 5/2. So what's your common denominator there? What's your common denominator? Your least. So the common denominator is the least common multiple of all these. 18, right? Which would be 3 squared times 2. So I've got a 2, and I've got just a 3, that's possible, and then I've got a 9, which is 3 squared. So it's the same idea here. Does that help? Yeah, so it's like we're kind of thinking backwards. It's like what would be all the possible denominators that when we add them together, we would get that common denominator, but we don't want to be redundant. We don't want to keep doing every combination so that we keep repeating ourselves. So this is what's necessary and sufficient, okay? To have just x minus 3, to have just x minus 2, but then also to have x minus 2 squared. Okay? So we didn't really talk about how I got these constants up here, but the reason they're constants is you want your numerator always to be 1 degree less than the kind of the structure or the base of the denominator. So this is x minus 3. 1 degree less is just a constant, a. This is degree 1. 1 degree less is a constant. But this is also degree 1 because the whole thing is squared. So you're just looking on the inside. So you have still a degree 1, so we can do C here. And now we're ready to start adding and go. Okay, so now we're saying that what we have inside the integral is exactly the same as this. So now we're going to add these together and figure out how it can be exactly equal to this. In other words, what A, B, and C will make this the same as this. Okay, so here we go. What I need to multiply top and bottom by in this first fraction to have my common denominator? X minus 2 squared. And then what about B? You need an x minus 3 and another x minus 2. And then C? So now we're adding. So we get the general form of our answer, but then we've got to add them. When I actually add the fractions to see how it's equal to what we started with. So this whole thing would be divided by the common denominator. Which is that thing, right? The x minus 3, x minus 2 squared. So now we got the denominators equal. So all we got to work on the numerator now. Here we go. Ready? So I'm going to multiply these out and distribute in the A's, B's, and C's. Ready? AX squared minus 4AX plus 4A plus BX squared minus 5BX plus 6B. Check my math. Plus 6X minus 3C. Or CX minus 3C. Okay, check my math. Did I do it right? I think I got it. Agree? Okay, and what does that whole thing have to be equal to? X squared plus 1. Because that's our numerator. So we're figuring out what A, B, and C makes that thing equal to the numerator we have, x squared plus 1. So now we're going to gather all the x squareds. Do that with a blue circle. Here's an x squared. Here's an x squared. Any more x squareds? So therefore, A plus B equals what? 1. Where did I get the 1? Right there. So blue is my x squared terms. A plus B has to be 1. We'll do red for the x terms. Red. Minus 4AX minus 5BX plus CX. Any more x terms? Okay, and how many x's do I have over here? 0x. That's my red. There's no x over there. Therefore, minus 4a minus 5b plus c equals? Did you catch it? And then finally we got constant. 4a, 6b, minus 3c equal to? 1. There's my constant, 1. Three equations, 3 variables. 3 equations, 3 variables. Again, whatever technique you want to use. You can do elimination twice. You can do some kind of substitutions. You can use a matrix method. However you know how to do this, you should know at least one way to do this. Yeah?
That first part, kind of, why didn't you multiply b by x minus 2 squared? Or c by
I'm asking, so I'm adding these fractions. So when you add fractions, you need a common denominator. And our common denominator is what we started with. So I'm asking, what do I multiply top and bottom by to get the common denominator? So if my common denominator is x minus 3 times x minus 2 squared, what do I need to multiply top and bottom by here to get that common denominator?
x minus 2 squared.
Right, and what about in this one? I've got 1 x minus 2.
So you just need 1 more x.
1 minus, and then I need the x minus 3. And then what do I need to multiply top and bottom by here?
Just x minus.
Make sense? Yeah. Other questions? Okay, so here's what I see. I've already got C eliminated here. So I'm going to eliminate C from these two. And then I'll have, when I eliminate C, I'll have another equation of A and B. And I can combine it with this one. And I'll got 2 equations, 2 variables. So I can get rid of the C's in these two by multiplying this one by 3. And I'll have positive 3C and minus 3C. So I'm going to take this second equation, I'm going to multiply it by 3 and add it to the third equation. And that'll make the C's go away. And then my result, I'll combine it with this. Okay, so when I do that, I'm going to get negative 12a and 4a. I think that's negative 8a. And then we're going to get negative 15b and 6b. I think that's minus 9b. And then I'm going to get 3c and minus 3c. That's what we wanted, 0. And then 3 times 0 plus 1. Okay, so when I eliminate c from the last two equations, I get minus 8a minus 9b. And now I'm going to combine that with the first one, the blue one. Okay, and you can use substitution, elimination. I'll go. What's that? That was my x. A plus 1 came from the x squareds, right? That's plus 1 right there.
The other one.
This here?
Yeah.
No, I'm adding. I'm multiplying this by 3 and adding the two equations. Because plus 3c plus minus c is 0. So I'm adding this equation to this one. I think it's right. Is it right? Yeah. I multiplied this by 3 and added it to the third equation. That made the c's go away. So I'm going to add 1. Okay, should I do just some substitution for something different? Or should I keep doing elimination? Elimination, here we go. So what I see for this is now to multiply this by 8. And let's eliminate a. Okay, so 8a plus minus 8a is 0. 8b and minus 9b, negative b. And then 8a plus 1. So I got b is negative 9. That would make a positive 10 from that first equation. And then is there an easy way to get c?
Last equation. A and B.
Maybe this one, since the c is already ready to go. So it would be 4a plus 5b. C would be positive 4a plus 5b. So 40, negative 5? Positive 5. Positive 5, thanks. Okay, so there is our values of a, b, and c. Okay, those will be fractions sometimes. These were not. We like that, but you were going to get some fractions for these coefficients. So now we know what we have exactly what this equals to in its decomposed state, right? It's going to be, I'm going to come back up here, 10 over x minus 3, minus 9 over x minus 2, 5 over x minus 2 squared. So now that is equal to what we're doing. Question?
Wouldn't C be negative?
We'll keep going back and forth here. So it would be, I think it would be plus 4a plus 5b. Plus 4a plus, yeah.
It's negative 4.
Uh-huh. Sure. I agree. So then we got negative here. Are we good now? Okay. All right, so then this is equivalent to our original integral. Okay, so let's just talk through it without doing it here. What's the structure of that antiderivative? Natural log. What about this? Natural log. What about this? Yeah, you just basically, you've got something to the minus 2. You basically just have something to the minus 2. So its antiderivative is that thing to the minus 1, right? And then you have a 5. And I think you'll get the negative from the exponent, right? So when you do negative 1 times 5, x minus 2 to the minus 2, I think that does it right there for that third one. So I didn't write the answer down. We just talked it through, right? This will be natural log. This will be natural log of something. And then this is 5 x minus 2 to the minus 1. Okay, let me just get one more, last one started here so you can do your homework. Any questions on that?
Sorry.
Yeah.
A, B, C, where did you go? I didn't get. You went like up to the integral.
Yeah, don't lose sight of what we're doing. We're trying to find those coefficients of that original expression so that that thing equals this.
Okay.
So I just put them in. That was my A, that was my B, that was my C. So I just erased and put them in.
So much easier, babe.
Okay, questions? All right, let's, one more. This one's different. So this only works, so we got the degree of the denominator is greater. This only works if you can separate out the denominator into factors. How does that for x cubed plus 4x? You can take an x out, and then you have x squared. If that were x squared minus 4, you could keep going, right? But you can't. X squared plus 4 does not factor any further. So we can still do this, but here, what's different now is that we have a quadratic factor down here. So we didn't have that before. We had a linear factor squared. So with a linear factor squared, we still just had the constant term up there. But now we truly have a quadratic factor down here. So when we do this, we're going to go a over x. What we choose for let's see. So this is what we're rewriting, okay? So what we choose for the numerator is always 1 degree less than the factor that we have. So 1 degree less than x is constant, but now this one is truly quadratic, x squared plus 4. So we're going to need bx plus c. So we need the most general form of a linear. So we have a quadratic denominator. We need a linear numerator, 1 degree less, so bx plus c. Okay, ready? We're going to make it. Here we go. So common denominator is x times x squared plus 4. Adding the fractions, top and bottom by. So a will be multiplied by x squared plus 4. This one will be bx plus c times, what do we need top and bottom here? X. So here's our numerator. And that has to be equal to what? We need a, b, and c, so that whole thing equals 10. 10, okay? So here we go. Ax squared plus 4a plus bx squared plus cx equals 10. All right, so a first, or x squared terms.
Why is the bx squared?
Because I'm taking bx plus c times x.
Oh,
Why you multiply by x?
Because what do I need top and bottom on this one to get the common denominator? What is my common denominator? It's x times x squared plus 4. So I'm going to multiply the top and bottom of this times x. Just like we've been doing the whole time. Just like over here, I multiplied top and bottom by x squared plus 4 to get the common denominator. So now I got to multiply top and bottom by x to get the common denominator. All right, so then how many x squareds do we have over here? 0. Therefore, a plus b equals 0. Quadratic in blue. Okay, linear in red. Where's my linear? Linear. How many x's do I have? 0. So therefore, no, just c equals 0. Just the coefficient. We like that. That automatically gave us one. And then finally, constant. That's the only constant for a equals 10. So this is easy. A equals 5/2. B equals -5/2. C equals 0. So now what we were trying to, this is what's equal to our original problem. We had to figure out what the A, B, and C were so that it's equal to 10 in the numerator. So we got a 5/2 over x, and then -5/2 x over x squared plus 4 plus 0. So let me just make some room here, and we'll do that. Here's the end of the problem. So 5/2 over x plus -5/2 x plus 0 over x squared plus 4. And then what's going to be, that's going to be the integral of that thing, because that equals what we started with, dx. Okay, so how do we do 5/2 over x? Natural log, 5/2 natural log x. And let's see if anyone's learned anything. How do we do -5/2 x over x squared plus 4? Undoing chain, because this here you have is essentially the derivative of what's in the denominator. So it's going to be -5/2, what? Natural log of x squared plus 4. But then we'd have to check this, and I think we have another 2, right? We're going to have a 2x, therefore, we need to the 1/4 here. If you have questions on this last example, I'll leave it up. I won't erase it. You can come up and ask me. But I will see you again not till next Monday. So we'll have 2 webworks, one on the more trig practice, and then these.